continuation from yesterday. And as we will recall, we had started a conversation regarding the electrophiles that can be used in both substitution reactions. I'm assuming that, well, it is my expectation that today will be the last lecture pertaining to SN1 and SN2. Anything else that we don't get to cover, I don't think there's much more that we won't get to cover here, but whatever else is left over may come to you in the form of a document or a handout or so on. But this is the last official lecture for this topic. Right, so remembering what we were discussing in our last class, you will remember that we had identified a series of reagents that could be applied in various contexts. So the table that is before you is giving a list of compounds that undergo substitution. Starting from the top, you can see that we have a primary alkyl halide that is known for SN2 reactivity. Now, the reaction that's being considered here is the solvolysis reaction. And if you remember what we were talking about a few moments prior, a few sessions prior, we had spoken about solvolysis as being the substitution reaction that occurs when the solvent molecule behaves as the nucleophile. Now, as it occurs, what happens here is we have a series of electrophiles. Here you have a primary electrophile, which we know are typically the most optimal electrophiles for SN2 substitution. Here we have a secondary electrophile, a secondary alkyl halide, which is ideal as well. And then here we have a tertiary alkyl halide. When the solvolysis rates were compared for these reactions, for these electrophiles, what was observed is that the rates are poor for solvolysis. Now, solvolysis is typically one that is interpreted as SN1 mechanism, because it is expected that the leaving group would leave first. And since the solvolysis reaction occurs by way of SN1 mechanism, that would explain why the relative rates are so poor for the electrophiles that are listed here. We are seeing that for the primary and secondary electrophiles, the relative rate is 0.07 as well as 0.12. And the reason why that occurs is because these electrophiles are not good SN1 electrophiles. They are prime SN2 electrophiles. Okay? So that's where these numbers are coming from, and that's why they're there before you. Going down the table, we are recognizing that there's a jump when the substitution pattern changes. And so here for our tertiary electrophile, what we observe is there is a significant increase in our relative rate, because at this point what's happening is you have a substitution pattern that is more appropriate for SN1. And like I said before, solvolysis proceeds via SN1 mechanism. So what about this electrophile here? As we observe, it is a primary electrophile, and it seems to have a relative rate that is 1.0, which is definitely at least one order or two orders of magnitude faster than the first electrophile, which is propyl chloride. Now, essentially what we're seeing is the result of the introduction of a double bond. And so I went through this the last class where I was explaining that allyl substituted electrophiles are more stabilized. So whenever there's an electrophile that has a pi system incorporated in its molecular framework, one will expect that the reaction will occur much more rapidly because it is more favored. And the reason for that is because you have a stabilized intermediary species. So the difference between the allyl chloride that is here and propyl chloride, which is at the top, is the introduction of this double bond. And this double bond makes a wide difference in terms of the outcome of the reaction rate, because we have p orbitals that contain electrons, and those electrons are able to stabilize whatever partial charge that would result. Okay? And the difference between this electrophile and this one, which is actually saturated, is that your carbon atoms do not have that type of facility. They are sp2 hybridized. And so the stabilization is not to the same extent. All right, I think that that's pretty much what I want to say concerning that. We have already spoken about benzylic and allylic electrophiles, so we're not going to go over that again. Okay, so moving forward, we are able to look at another group of electrophiles and observe them more carefully or more closely. And here we have a comparison that is being made between primary electrophiles, tertiary, allylic, benzylic, and a whole host of others. So let's take a look and see what's going on here. In this reaction series, the electrophiles are being compared according to their performance in an SN2 scenario. So here, instead of the solvolysis reaction that we were looking at before, we are now seeing a different type of reaction. We're looking to see what happens in an SN2 mechanism. So here we have a typical SN2 process where you have butyl chloride being substituted by iodide. Okay. Being substituted by iodide as a nucleophile. And so the iodide is going to do what it is expected to do by attacking the carbon center that bears the chlorine atom. The resulting product is butyl iodide and your byproduct chloride. So the question is, how do the other electrophiles perform under the same type of conditions? And so what we are seeing is when the electrophile is changed to methyl chloride, the rate of the reaction increases by 200. And so that's why this number is circled here. Once the substitution changes, once the substitution pattern changes, in that we actually now go to 2-propyl chloride, where we have a secondary electrophile, the substitution pattern impacts the relative rate, causing our reaction to actually slow down. So here, the reaction rate has actually changed significantly in that it is even slower than the original reaction that is identified at the top here. Again, we see a similar increase as discussed in the previous slide, with allyl chloride. And here we are seeing the numbers bear witness to that, where it is not as fast as methyl chloride, but it is definitely faster than the secondary chloride that is observed here in 2-propyl chloride. Okay. All right. Now looking at the benzyl chloride, which is the 4th electrophile on this chart, we are seeing that there's an increase in stabilization, and that increased stabilization allows then for the reaction to proceed just as fast as if you had methyl chloride as your electrophile. So in other words, this benzyl chloride is actually reacting faster than butyl chloride as an electrophile. And it does proceed by way of SN2 mechanism. We know that because here your chloride is primary in substitution. Okay, now making an additional adjustment where we introduce the heteroatom to the same electrophilic carbon causes a definite dramatic increase in the reaction rate. And the reason that we would have seen that as being the case is because we have what we call electron donating groups. We saw this before, and so this is another example of it being present in our reaction sequence. And then finally, we are observing that if you have a carbonyl system conjugated with a phenyl ring, that's a whole lot of p orbitals that contain electrons in them that are able then to basically share their electron density with the depleted electrophilic carbon that's present here. And that is why we are seeing this dramatic increase in terms of reaction rate. So the take-home message here, guys, is that once you have increased numbers of electron donating substituents, your intermediary species are more stabilized. And once your intermediary species are stabilized, that will cause, one, your activation barrier to go down, and two, your reaction rate to go up, because it means your rate constant has actually been increased. Okay, we can move forward in our presentation and take a keener look at SN1 and SN2 electrophiles in summary form. So the general idea is methyl electrophiles work best for SN2. They are poor for SN1. Okay. For obvious reasons, the carbocation intermediate is the worst when it's in primary form, unless it is in those scenarios that we just discussed. And then we have other electrophiles that are not methyl substituted, but are primary substituted electrophiles. Those work well for SN2, and again, poor for SN1. They don't react at all unless there are additional features. And so we continue on, and we are able to see that secondary alkyl electrophiles work well both for SN1 and SN2, because at this point we are getting into the crossover period with regards to electrophilicity. Our tertiary alkyl substituents or electrophiles work very well for SN1 but poor for SN2. And the reason for that is because steric bulk becomes a problem. If you remember, the mechanism of the SN2 reaction is a bimolecular mechanism, which means that the reaction depends on the nucleophile and the electrophile coming in contact with each other in the rate determining step. So if the electrophile is bulky or if the nucleophile is bulky, access will be hindered and that will be a problem. So that's the reason for the no here. Allylic electrophiles give us good SN1, and that means that in spite of the fact that you may have a primary substituted carbon where your leaving group is attached, once you have your adjacent double bond, you will be able to access the SN1 mechanism. However, SN2 is also possible with those electrophiles. Similarly, we can say the same thing for benzylic, and that's the ones we saw a few moments ago. Same outcome, really good with SN1 reactions. It's pretty decent with SN2 as well. Now, why am I highlighting this? I'm taking a moment here to just give you guys a little insert at this point to say that the reason why this is important to know is because if you were to have a reagent that is in either of these two categories, you will find that the product will be a mixture of enantiomers because SN1 is a non-stereospecific reaction mechanism. And so even though it would be a primary electrophile, and you may say, well, I expect this to proceed by way of SN2, the reality is that SN1 products would also result. Okay? So it's not exclusively SN2 then. If you have an alpha carbonyl, that means if you have a carbonyl present in the alpha position. So what does that look like? That looks like an electrophile that has a carbon with a double bond. And here is your leaving group. That is what your electrophile would look like. If you have that, then what's going to happen is it will proceed excellently via SN1, but poorly. Wait, what am I saying? No, I'm looking at the wrong thing. Yeah, it proceeds excellently via SN2 and not at all for SN1. So in other words, the substituent, I'm going to draw this over here where we can have better lighting so that you guys can see. So your alpha carbonyl electrophile is one where let's change that color. Is one where your leaving group let's say we have something like this. And this is where our leaving group is. This electrophile will work well for SN2. And it will not react at all for SN1. Okay? So let's just erase that. Right. Now, if you have an alpha alkoxy, meaning, again, let's look at the structure of our electrophile here. Alpha alkoxy means that we have the CH group. Here is our leaving group. Here is the hydrogen atom. And here is an oxygen atom that is able to donate electrons. So here, this is supposed to be an R. Right, so this is your alpha alkoxy. So this group here is looked upon as EDG, meaning electron donating. And the previous group at the top where you have an alpha carbonyl is actually what we would call electron withdrawing. So EWG. Okay, and so that's the reason why there's a switch here. Okay, so let's tidy this up and we will revisit this. You will see more of this as we proceed. Okay, now alpha alkoxy electrophiles and alpha amino electrophiles tend to behave the same, and so the same rules apply. They work well for SN1 because they generate a stabilized carbocation. We saw that previously. And they're decent for SN2, but not as excellent. So the take-home message here is that there are some electrophiles that can react well for both sets of mechanisms, and the question of which mechanism to apply under what conditions will be determined by what you know about the intermediates and your reaction conditions. So let me just give a little bit of insight with that so that we can know how to distinguish them. Right, so since we have some mechanism, since we have some electrophiles that are sort of straddling the fence, we can identify conditions that distinguish them, okay? That would be an important distinction for us to make. So let's look at the ones that are overlapping. So our secondary alkyl group has both SN1 and SN2 capability. Our allylic groups have SN1 and SN2, as well as our benzylic. And then we have alpha alkoxy and alpha amine. So these sets of electrophiles are able to undergo SN1 as well as SN2 reactions. The others are pretty straightforward and clear, and you need to know them. You know those as, okay, this is an SN1 electrophile. We know that this is an SN1. We know that the tertiary is SN2 exclusively. And then we know the alpha carbonyl is SN2 exclusively. So for the ones that are sort of straddling the fence, what would then be the distinguishing components that actually separates them from each other? Well, For these electrophiles that are actually able to do both mechanisms, the way we would be able to identify which mechanism is applicable is by looking at our nucleophiles. Okay? Once we look at our nucleophiles, then we're able to tell. Now we know that the SN2 reaction requires strong nucleophiles. And strong nucleophiles come in the form of specific criteria. So strong nucleophiles equate to strong bases, and strong bases tend to be charged non-resonance bases. So your strong nucleophiles would be things like your halides, your hydroxide nucleophile, your alkoxides. I think I'm supposed to change that. Yeah, your alkoxide, your amides. Now, amides is a term that you see in organic chemistry being used in two different contexts. There's the amide that has the carbonyl, and then there's the amide that is actually a deprotonated nitrogen molecule. So this would be amide. As well as other substituted versions of it. Sulfides, okay? These are all examples of strong nucleophiles. And notice that among them, there are no resonance structures. That means that the electron density is heavily concentrated around the nucleophilic atom. So once you see these types of nucleophiles in your reaction mix, you know that the mechanism will proceed by way of SN2. Now, if your nucleophile is the conjugate acid of these, so for example, if you have water or an alcohol, or let's say a protonated amine like ammonia, then you know that your nucleophile is neutral, it's weak, and that's appropriate for an SN1 mechanism. So those are your main clues, okay guys? Make sure you know that this is a distinguishing feature and it's an important one that helps you to determine what mechanism is at work in the process that is before you. All right, so we already spoke on this. We said that electron donating groups, once your carbocation or your intermediate species has an electron donating group, then you are likely to find that the reaction will proceed via SN1, and that's what bears out here in your allylic, benzylic, alkoxy, and amino electrophiles. Your carbonyl proceeds by SN2, and that's because the carbonyl group is an electron withdrawing group. Okay, so comparing SN1 and SN2 rate constants, we are seeing this again. Here you have a plot of the various electrophiles and how they vary in their performance. And so, for example, we just spoke on that in another way. And so this graph basically just repeats what we have said already. Before we continue further, I just want to make a quick distinction because, as you know, every reaction proceeds by way of a reaction profile or has a corresponding reaction profile that is applicable. Essentially, what it means is the reaction profile is the energy picture of the species in the reaction itself. And essentially what we are doing is we are looking at how the various species in that reaction process vary in terms of energy once the movement is from reactants to products. So here we have a picture of the reaction profile of a typical SN2 reaction. And you can see the different components highlighted. And so we have the activation energy, which is represented by the difference in energy between your reactants and your transition state. That is the basic energy hump that has to be overcome in order for the reaction to take place. We know that the higher the activation energy, the slower the reaction will be. We know that the lower the activation energy, the faster the reaction will be. And that's because there is a direct correlation between activation energy and rate constant. However, what we have not paid much attention to is the difference between the energy of the reactants and the energy of the products. Essentially, when we think about the differences in energy between those two species, what we have is the possibility of two occurrences. In the first case, we have the scenario where our reactants are lower in energy than the resulting product. Those reactions that come under this category are referred to as endothermic reactions because there is a net absorption of energy that is required in order for the reaction to take place. It doesn't matter though that you have these two differences because the reality is that the activation barrier of the reaction itself is what is needed to be overcome in order for the reaction to proceed. So irrespective of the fact that you have a difference in the energy between products and reactants, the determining factor is the activation energy. On the other hand, we have the option of there being a higher energy level for the reactants and a lower energy level for the product. And in that case, your delta H is such that you are releasing energy to the environment. And this is what we would refer to as an exothermic reaction. This is just a distinction that I wanted to highlight because the reality is that while you can focus a lot on activation energy, there is an important component as it pertains to energy released or energy absorbed. The last thing I'm going to say on this is the impact of catalysts. We know that a catalyst speeds up the rate of a reaction. It can also slow it down, but it speeds up the rate of the reaction. And the way it is able to do that is by actually being able to lower the activation energy of the reaction. So in the presence of a catalyst, your activation energy is decreased. And once it is decreased, there are more molecules that are able to access this energy level. And hence the collisions that they are able to endure or encounter would be more, which would then cause the rate increase that you see. Okay. So now to the real meat of the matter. It is at this point now, guys, where we are going to really get into why these reactions are so important. And it would bring us back to that first slide that we encountered when we started this section of the course. we had done structure and bonding initially, where we were looking at the structure of the carbon molecules and all of that. And now we are here to actually explain how that structure influences the behavior of the carbon atom in terms of an atom by itself, and then now further to that, how it influences the behavior of the carbon atom in the context of a molecule and other compounds. So we know that chemical building blocks are all a part of our life. There is no chemistry without the building blocks that chemistry is able to afford us. So what that means is we are able to now build our library of chemical reactions and use that library to help to afford us various types of chemical compounds. And so we have been introduced to two sets of reactions thus far that enable us to be able to access a wide range of compounds. These compounds afford us the ability to be able to then diversify and build molecular complexity and understand how complexity is built in other systems. So we have here on the left our blocks that contain nucleophiles and electrophiles. And here we have generic conditions that will vary according to the specific context that is needed for the products that we want. And of course, in the second box is the list or a jumble of many types of products. Right. So this is where our library of SN1 and SN2 reactions now begins to take shape. If we have our electrophile, let's just designate our electrophile Rx, we are able to use a different set of tools and actually apply specific conditions to afford us various classes of compounds. So here is an example. If we have an electrophile designated Rx and we subject Rx to conditions that include the use of nucleophiles such as NHR, which would be an amine, or the amide version of that, we would be able to access a class of compounds known as amines. Continuing forward, we are actually able to continue to expand our repertoire of molecules and their complexities by using a different set of reactive agents. In this case, if we change our nucleophile to sulfur nucleophiles, we are able to access ethers or thioethers. Adjusting again our reagent pool, we're able to access haloalkanes, oxygen ethers themselves, and thiols and alcohols. So I think by now you get the picture that by simply varying the conditions in terms of the reaction components, we're able to access a wide array of compounds. And once we're able to access those compounds, we're in a position to be able to build molecules from the ground up and actually just stitch them together in interesting and creative ways. So here are some examples then, real life examples of how this takes shape. So we have a situation where at the top you have a cyclohexyl molecule that is substituted with a methyl group and an iodine group. Obviously, when we look at this molecule, we can see that it is an electrophile. And the electrophilic center is here. And of course, the iodine represents our leaving group. So these are important features to note because this is going to tell us where our reaction center is and where the reaction will be taking place. Of course, when we look at the reaction conditions, we can tell that it's a nucleophilic reaction. And this nucleophilic reaction is indicated to us because we have the presence of a sulfide anion. Now, this sulfide anion is a very good nucleophile, and that's our clue that tells us that it is an SN2 reaction. Now, having established that that's the kind of reaction that will take place, we then are in a position to invoke the appropriate mechanism that will give us the product of interest. So here, backside attack affords us attack on the electrophilic center and concurrent or concomitant release of the leaving group, which then gives us the inverted product in terms of stereochemistry plus byproduct iodide. Okay? Now, the second molecule is at the bottom. And here, what we have is a different, we still have an electrophile. Obviously, it is alkyl substituted. You can see that it is also secondary. But we now have the option of determining what is the mechanism here. Again, our clue that gives us an indication of the mechanism is the nucleophile, because this electrophile is one of those crossover electrophiles that can either go SN1 or SN2. The fact that we have a nucleophile that comes in the category of weak nucleophiles is our indicator that the reaction mechanism is most likely SN1. Okay? And so once it is SN1, it means that the products that we get will be actually the racemic mixture of the product, the substituent coming above the plane of the board as well as going behind the plane of the board. And these are expected to be in equal proportions. So by virtue of this change in reaction conditions, we have two different compound classes. We have thioethers and ethers that would have been afforded by way of this process. Right. Here is another example of a reaction sequence. And here we can see in the first case, you have a diol. This is a 1,3 diol that is reacting with sulfuric acid first. And the reason for that is because oxygen, OH, is an excellent nucleophile, but that would make it a terrible leaving group. And so, of course, it would have to then be adjusted or modified so that the reaction can proceed. And this is what we were seeing last class when we observed the mechanism of the SN1 reaction. So we are converting the OH into a good leaving group, and it, having been converted, is now susceptible to attack by our nucleophile. In this case, the nucleophile would be a Br-, which can then displace the water molecule, and you have what we see as a hydroxybromide. Repeating this reaction again leads us to the 1,3 dibromide. Okay? So, we can also continue by synthesizing an alkyl halide from an alcohol. That was the first one we saw just now, and we're seeing that again being repeated here. In this case, it's a secondary alcohol that's being used. There are other methods of synthesizing alkyl bromides from alcohols. If you notice, the course outline would have referred to some of them. This is one where the attack is occurring by way of using triphenyl bromide. And initially you see oxygens lone pairs attacking the phosphorus as an electrophilic center, and this electrophilic center is behaving like a carbon atom as we are accustomed to seeing it happen, except that now you have phosphorus displacing bromine. Here we have that intermediate resulting, which is the phosphorus bromide species here, which is then a really good leaving group. This is another example of activation. And then displacement by the bromide nucleophile to give us the alkyl bromide. So leaving group activation is something you have just observed. And in this case, the general idea is when you have a poor leaving group such as OH or hydroxide, it is important to note that those poor leaving groups have to be converted into a better leaving group, and they usually are done so by changing them, by actually reacting them with something that would turn them into that type of species. This is an example here. It's a typical one that occurs in living systems, and in this case the molecule tosyl chloride or toluene sulfonyl chloride is being used. Again, in this case, we have electronic attack on the sulfur. I think I actually have a slide with that, so let me just show that. Whereby you have attack on the sulfur that pushes out electrons from the sulfur oxygen bond onto the oxygen, and then that pushes back electrons from the oxygen back onto the sulfur, kicking out your chlorine, which we know chlorine is a good leaving group. And so the chlorine has been replaced by the oxygen. Finally, guys, for today, here is an example of a synthetic sequence where this species is being used. We have our conversion of our oxygen into a good leaving group by what we call tosylation, and then we are displacing it with our nucleophile, right, which is coming in the form of iodine, and then the iodine is then being reacted with triphenylphosphine to give us the phosphonium salt. This is then further applied in reaction sequences to create molecules. Guys, I think this is a good place to stop, and so we will not proceed at this point, but whatever else has not been covered will show up in the 2 hours that I said I will present to you. So look forward to that. You're going to get that this weekend. At this time, I want to take a poll and hear from you guys. If you're interested, I am available to give a tutorial this afternoon. I know we had a holiday this week, and so there are persons that had expressed an interest, and now would be your time to speak. I am going to stop sharing my screen now and pause or stop the recording at this time. Okay.